that's a good discussion. Let's move on to today's lecture, which is about basics of linear algebra. And we are not going to cover like a lot of linear algebra, but only those topics which are relevant to this course. So let me walk you through like the brief outline, the topics which we are going to cover. We are talking about, we'll talk about vectors, matrices. We'll talk about transformations which can be done on these vectors using the matrix. And finally, we'll briefly cover this topic, singular value decomposition. Okay, so before talking about vectors, we should know what a scalar is. So scalar is like any number which is from like which is some real a set of real numbers, and it's just like a single entity. And if you combine a lot of such scalars, you can form vectors. And depending upon like how many such entities you gather together, it will have some kind of dimension. And there can be two type of vectors. You can have row vector, where you arrange like these numbers in a row, and then you can have column vectors, where you can arrange these numbers in a column. And of course, you can describe like this column vector in form of a row vector. If you put a T sign here, this is called transpose. And I think we'll talk about this operation for matrix as well. And transpose is like, if you have a column, you can transpose it to a row vector. And if you have a row vector, you can transform it to a column vector. So it's just a notation. Now, let's briefly talk about where exactly we can use these vectors when we are dealing with like deep learning or machine learning. So if you have some kind of data where you have some set of values, so you need to store those values in memory, right? Then you will need vectors. And these values could be feature vectors, which you have extracted maybe from some images or maybe from some videos. And these vectors can also store like your actual pixel values from the images or videos. And it can be any other data like which you have obtained after performing some kind of processing on maybe the features or the pixels which you have obtained from images or videos. Now, this vector also represents, if you have a coordinate system, it also represents any point in that coordinate system. And depending upon like how many axes you have, it will be that many dimensional long. So if it's a three-dimensional coordinate system, it will have 3 dimensions. And so this is a point, and you can represent this point using a vector. Now you can also use the vector to represent distance between 2 points. So let's say we have another point, y1, y2, y3 in the same coordinate system, then you can use a vector to represent the distance between this first point and the second point. And if you want to represent that, it will be simply subtraction of the elements of the first vector and the second vector. Okay, let's now see like what kind of operations we can perform on vectors. The first one is norm. It indicates like what's the size of the vector, and it's used widely when you are coding in deep learning. And there are mostly use 3 kind of norms. So first I will just talk about the general form of norm, which we call P norm. And that's the formula for computing P norm. So for each element of the vector, you raise it to the power of P, and then you sum all the values, and then just take the root, the time root of that. So that's the general notion, but you can have any value of P ranging from 1 to like any larger values. So we call Euclidean norm when you have P equals to 2, and you just replace P with 2. And again, it's used, I think mostly this is used when you have your loss functions, when you compute in your models to train them. And a more general form, which is like derived from Euclidean norm, which is used, we call it squared Euclidean norm. And in that case, we just ignore this square root, and we just compute squares of each element and sum those values. So the benefit of that is when you're training your deep network, you have to calculate like a lot of derivatives. So whatever loss function you have, you will have to compute derivatives to train it. And we will cover that when we talk about deep learning, but just to give you in context. So what will happen is if you don't have the square root over here, then all the elements of this vector, when you compute the derivative, they will be independent from each other. So it's much faster as compared to when you will have a square root, where you will have that dependency. So that's why the squared form is used. The other important norm which is widely used is L1 norm. And in this case, you just take the absolute value of each element in that vector and then just sum those values. The other important operation in vector is inner product. It's also called dot product. So you have two vectors. When you take inner product, you will just get a scalar number. And the way to do inner product is you just multiply the corresponding values between those two vectors. And the notation is you first have to take transpose of the first vector. So it becomes a row vector. And then you put here like the column vector and then take multiplication. So essentially what's happening is it's kind of matrix multiplication, but your matrices, the first one is, it just has a single row and the second matrix just has one column. So you just multiply these two vectors element wise and sum those values and get a scalar. Now, if you think about this, if you take inner product or dot product of the same vector, where the first one is the transposed one, so that will happen, and it's actually square norm of x1. Because you're just multiplying the same element of the vector to itself, which will give you the square. And since you don't have the square root, it's the squared norm. So this is the form which I like just discussed that it's used widely. So that's another interpretation you might find useful later on. And another interpretation of dot product is you just take norm of those two values and it's called, so in this case, what's happening is so these are vectors, right? And there will be some angle between these two vectors. You take cosine of those two, cosine of that angle, and just take absolute values of these vectors. So it's also called a cosine distance. And a special case of this is when your second vector is a unit vector, which means like it has unit length, then a nicer interpretation of this is it gives you projection of the first vector along the direction of the second vector. Now, what will happen here? So if this is unit, this will be 1. So this will result in x cos of theta. And in this case, so x is a, the first vector. You just take cos of theta. So you will get this projection from this point to this point. And this will like come back later when I try to explain like different form of transformations in vectors. So now, so that was inner product. The second is outer product. And in this case, the transpose operation is done on the second vector. So the first one will be the column, the second one will be the row. So what will happen is it will result in a matrix because you are multiplying like those two elements from these resultant row and column vectors every time. And every time you multiply, you will get a value for the matrix. So now talking about matrix, it's just like an array of numbers and it can have different shapes. So when we say like a matrix is m by n, it means like we have m rows in that matrix and n columns. So this is just showing a sample example. So you can see that index m here, which implies that you have m rows and n columns. And as we talked before, row vector is nothing but you have single row, that's a row vector, and a column when you just have single column. So those two can also be represented as vector, as matrices. Now, why we need metrics? So some of the uses. if you have an image, you can represent that image in form of a matrix. And I think we covered that in the first lecture as well. So what will happen is each number in that matrix will represent one pixel. And if the resolution of that image is n cross m, we'll get an n cross m matrix. And of course, like if it's one number, it will have to be a grayscale image. So this is the same picture from lecture 1. So if we just take a patch from this image over here, if it's 10 cross 10 pixels, then we'll have 100 different values. And similarly, like the full image can also be represented by that huge matrix. And it will depend on like what's the resolution of that image. Now, if we have colored image, so we should have 3 channels. So we'll have 3 different matrices, or we can also say that we will have 3-dimensional matrix where we'll have like n dimension in the first for the first channel, m for the second, and 3 for the last one. So instead of 1, we'll have 3 different matrices, and you can club them together to make like multi-dimensional matrix. Okay, now let's talk about the operations which can be performed on matrix. So addition, that's trivial. So if you're adding 2 different matrices, you just sum the corresponding values which are at the same location. And one requirement for this will be the shape of the matrix should be same. So if it's not same, then you will not be able to pair like these values. And the only so you can do the addition even with scalars. So this is like implicit. If you just add a scalar, you can convert that to a matrix of the same shape and just repeat this value and add like the corresponding values which are in the same location. And the same rule applies with subtraction. So this is fairly simple. Similarly, you have scaling, where you multiply the matrix with a scalar, and the same scaling operation is performed on each of the values. Now we have Hadamard product. So this is actually very useful when you're working on deep learning. So this operation is required when you have to like play around with your features, and it happens a lot that you have to do element-wise operation between the features. So this will be used widely when you develop your models, and this is not like a very difficult thing to understand. It's just like element-wise multiplication, but yeah, it's used widely. So okay, so matrix multiplication. This is a bit complicated than addition, subtraction, and scaling we have seen. And I think you all must know this, but let me recap it for you. So if we have a matrix A, which has in this case, it has like 4 rows and 2 columns. And if we have a matrix B, in this case, we have 2 rows and 3 columns, and we are going to multiply this. So the resultant will be a matrix, and what will happen is each element for each of the location in this matrix can be obtained by multiplying the corresponding row from the first matrix with the column of the second matrix. So for example, this location, if you try to figure out the indices, this is first row, second column, so it's 1 cross 2. So we'll take the first row of the first matrix and second column of the second matrix, and then you will do element-wise multiplication, and then just sum those values up, and you can obtain the value for this particular location, and same goes for this. So the operation is not that difficult. So what you need is 2 matrices need to be compatible. So for example, when we are doing addition, the restriction was both the matrices should have same shape. So in multiplication, that's not the case. Of course, like if the matrices have the same shape, then we can do the operation. But even if it's different, even then it's possible. So what's the requirement? The requirement is, since you are doing element-wise multiplication of rows of this matrix with columns of this matrix, which means the number of elements in the rows should be same as the number of elements in this column. So it means like the number of columns in this matrix should be equal to number of rows in this matrix. And then we call that these two matrices are compatible for multiplication. So the first matrix can be m cross n, then the second will have to be n cross something else. And this m and p can be anything. It's just like this n has to be same for both the matrices. And this will result in m cross p. So you can see that if the matrices are square matrices and have same shape, then also it's possible. So that was basic. Now let's try to see like what are the other interpretation of matrix multiplication. And this is more interesting and I think also relevant for deep learning. So we will talk about like different interpretations. So this is the first one. So let's say you have two matrices A and B. For the first matrix A, what you will do is you are going to denote ith column of that matrix with AI and the jth column of B with BJ. So what you have now is you have two matrices. So each of these each of these like represent one column for both A as well as B. So in this case, you have n columns and you have m columns here. Now, if you have to multiply these two, then what you can do is you can simply take transpose of this, the first matrix, and multiply with B. So the resultant matrix will be, you just take transpose of the first column and take a dot. So this is a dot product and multiply it with B. Now what is happening is, so earlier we saw that to get each element in a matrix, you have to multiply row from first matrix to column with the second matrix. So when you take transpose of this, these columns are going to be converted to rows. So then A transpose will have A1 transpose as the first row, A2 transpose as the second row, and so forth and so on. So to get the first element here, you'll have to multiply that vector with the first column of this matrix B, and that's what's happening here. And similarly, you can obtain like other values here. So again, it's the same operation, just like a different interpretation. So let's see like what are the other interpretations. And this is like my favorite, and there's reason to it because it gives you intuition like what actually is happening. It's not like just multiplying numbers and getting some values. It's actually trying to explain what's happening at a higher level when you're doing matrix multiplication. And it's useful when you are developing your model and you have to perform some operation where you know at a conceptual level what you want to obtain. And if you understand this particular interpretation, I think it's very helpful. So let me try to explain it to you. So again, we have two matrices, A and B. Again, we are representing them as like set of columns, again, set of columns. And if we multiply them, so this time it's not A transpose, it's just A times B. Now, in this interpretation, what we have is, if we want to get the first column of A multiplied by B, so that is represented as a linear combination of all the columns of A. So if we multiply A with B, we'll get a matrix, all right? And in that matrix, you will have first column. So how to get that column? So that column is nothing but a linear combination of all the columns of A. So by linear combination, I mean is these columns will be added to each other and they will be weighted using some number, and that weight can be obtained by the elements of this first column B. Okay, so this B1 column will have n values, all right, because if it's not n, then we cannot multiply these two. So we can represent those numbers as B11, B12 up to B1n. And what's going to happen is we will multiply the first number with the first column, the second number with the second column. So, and then we'll add up those columns, and that will give you the first column. And similarly, you can obtain like the other columns. And again, so again, it will be in a combination of all those columns, but it's just like the weights you are using for that combination. It will be the second column of the second matrix. So let me try to elaborate this further. Let me see. Okay. So let's talk about this particular value in the resultant matrix C. So to obtain this value, what we have to do is we have to multiply this row with this column, all right? And then we can get this value. Let's see how we can get this value. So this value we'll get when we will multiply this row again with the same column. For the next value, again the next row with the same column. So what's happening when you're multiplying all these rows with this column, so the first value is always getting multiplied by this number. So whether the value is on the first row, second row, third row, it doesn't matter. So all these values are getting multiplied by this number. So this we can represent as A1 times B11. So B11 is this first number, and A1, so instead of writing these values separately, we just form a column vector. Okay, so this first term arises from this column scaled using this value. And similarly, this column will be scaled using the second value, and the third will be using the third value. And that gives you this linear combination. Okay, and similarly, like, so this is just the first column. And if you have to get the second column, you can just repeat this process. Now, so this was linear combination of columns of the first matrix. How about if we have to do linear combination of rows of the second matrix B? And it's almost similar, but I will still walk you through it because it can be tricky sometimes. Now, in simple text, so in the previous interpretation, you had like you were actually looking into columns. This time we will look into rows. So each row in the resultant matrix is a linear combination of rows of matrix B. And let me walk you through this again. Okay, so this time we are looking at rows. Now let's again see like how we can get this number. So this number can be obtained by multiplying this row with this column, right? And how do we obtain this number? This number can be obtained by multiplying again this row with the second column. So it's almost similar, but instead of looking at rows of this matrix, we are columns of this matrix. We are looking at rows of this matrix. Now you must have figured out. So when you're multiplying this column, this row with the first column, then this particular number is always getting multiplied by these numbers. So instead of writing that separately, what we can do is we can represent this first row as a vector and then just do a scalar multiplication with this value, which is A11. So this B1 is this first row here. All right, so what will happen is you will multiply this row with the first number, then you are going to multiply the second row with the second number, third row with the third number, and you just take the linear combination, you get the first row. Okay, so now transpose, we saw that earlier when we were transposing vectors, but we can also transpose matrices. And in transpose, so we have indices I and j in a matrix, we just interchange the matrices. So this number here will come at this location. So because it's 1, 2, it will come to 2, 1. Similarly, if it's 1, n, it will come to n, n1. Now that's okay. The other operation is determinant. It's kind of give you like the size of the matrix. And again, it will give you a scalar. If it's a 2 cross 2 matrix, then determinant of A is simply multiply A with D and subtract with B cross C. So that's just the notation. And you can also compute determinant of higher dimensional matrices. And before going to that, let me talk about what's the interpretation of determinant of a matrix. So if we are in a two-dimensional space, then when you compute the determinant of a matrix, what it means is it's trying to compute this area, and this area is of a parallelogram, which is formed where like the coordinates are formed by the vectors we have in this matrix. Right, so this AB is like the first vector, this one, and CD is this second vector, and you create a parallelogram using these two vectors that will give you some parallelogram, and determinant is just the area of that parallelogram. And the same notion like applies when you have higher dimensional matrix, but like if it's too high, then I mean, you can't visualize it, but the interpretation is not going to change. Okay, so how to compute the determinant if it's like it has a higher dimension, it's more than 2. So what we have here is we have a cofactor, and when the matrix is 2 cross 2, the cofactor is just like one number, but when it's more than 2 cross 2, then cofactor is again a smaller matrix. And let me see, like I should have a visual for this. All right, so this is a 3 cross 3 matrix. If we have to find a determinant, so what we will do is we will multiply A with this particular matrix. So this is called the cofactor of A. And then we'll subtract it. Then we have the second number B, and the cofactor of B is this matrix, which is D, G, and Fi. So basically, to get the cofactor, what you do is you exclude the numbers from the same row and the same column. So in for this particular case, when we are computing the cofactor for A, so A is in this particular column, so we won't like include any of these numbers, and it's part of this row as well, so we won't include any of these numbers. So whatever is remaining, that's the cofactor. So let's talk about B. So it's in this particular column, so we will ignore these, and it's in this particular row, we'll have to ignore these. So the remaining elements are D, G, Fi, and that's the cofactor for B. And this can be generalized to like higher dimensional matrices as well. It's just like the cofactor will be, instead of 2 cross 2, the cofactor will be 3 cross 3 in case we have 4 cross 4 matrix. And the same formula will be applied. And some properties of determinant. So if you have to compute the determinant of multiplication of two matrices, you can compute like determinant independently and then multiply them. It won't change. And it's also commutative. If you're computing determinant of A cross B, if you compute determinant of B cross A, it will be similar. Similarly, like if you compute determinant of a transpose of a matrix, it won't change the value. So these are some simple properties which will be useful later on. So trace is another, okay, let me see. There is some chat, let me see if there are some questions. Determinant of A. Oh, I think there's some typo. So yeah, I think it should be AD minus BC. So that's a typo. So the other question is, what was the alpha value next to the cofactor? So let me go to the previous slide. Where is alpha? So Furkan, can you unmute and?
On the first line of right under the determinant. Determinant of, yeah, over there. Like what was that alpha ij?
Where is alpha?
Isn't that alpha next to C?
Oh, that's A.
A. Ah, okay.
That's this element A. So in this particular case, the first element.
Ah, okay.
Okay, so this is like just another operation. You can compute trace of a matrix, and it's simply like summing the diagonal values. So if you have a matrix like this, then if you sum up these values, that will be trace of this matrix. And again, trace of multiplication of two values is like commutative, and trace of like if you add those two matrices, the trace is not going to change. So again, these are like easy to prove as well. Okay, so this is another interesting property, not property like this is something which I think you will face when you compute eigenvectors and eigenvalues. Now, inverse of a matrix is it's denoted by this negative sign, and what it means is if you multiply a matrix with its inverse, then you're going to get an identity matrix. And identity matrix is like just once in the diagonals, and inverse does not always exist. So if you don't have any inverse, we call that singular matrix. And if you have an inverse, that's called non-singular. And these are some of the properties. Again, if you take inverse of an inverse, you will get the matrix back. And if you are taking multiplication, then you have to swap like the inverses to get the same value. So symmetric matrix, that's fine. If you take the transpose, the matrix will not change. It means the upper right part of the matrix is same as the bottom left part. Skew symmetric is almost similar to that, but you have a negative sign here. Sometimes this is also useful. So diagonal matrix is you don't have like any values in the off diagonal locations. All of them will be 0. You'll have values only along the diagonals. And this is like the identity matrix, which we were talking about earlier. When you multiply like a matrix with its inverse, you get an identity matrix. So this is like all ones across the diagonal, and everywhere else it would be 0. All right, so now let's talk about some of the transformations. Okay, so basically we will talk about transformation of vectors instead of matrices, and we are going to use matrices to do those transformations. And so if this is any transformation can be represented by multiplication of a matrix with a vector, and we call this resultant vector like the transformed version. So this matrix A will have to represent some kind of transformation which we are interested in. And the idea here is, given an input vector, after performing this transformation, we'll get a vector which will have that transformation. So this is like, even though this is a vector, but again, you'll have to do this matrix multiplication. Now, so scaling is one transformation where we just want to scale the values of the vector. And I'm calling it vector, but you can just also visualize that as an entity. So it could be like any object, or it could be any shape. So if you are going to scale that shape or scale that object, and then we'll have to perform this kind of operation. And of course, this is just a vector, but it could be a matrix as well. So for scaling, so this is called scaling matrix. So the of diagonal values will be 0. This is a diagonal matrix, and these values are the scaling factor. And these scaling factor can be similar. It just says that how much scaling you want to perform on each of these elements. So if you do the multiplication, you can do the math, you will get like sx times this first value and sy times the y. And this is, you can see, we're just scaling these values. Now, if we talked about one kind of interpretation where we were looking at matrix multiplication as linear combination of columns. So this is almost similar. What you're doing here is you have this matrix, you have the columns, and to get the column, you will have to do linear combination of these two columns based on whatever values you have in this particular column. The first column is getting multiplied by x, and the second is getting multiplied by y. So since we have zeros on the off diagonal, so all the other values from the columns will be ignored. So each column will only give you that particular value if it matches with the index of that diagonal. Okay. Now another interesting transformation is rotation, and this is like a bit complicated than scaling. Scaling was simply just like multiplying with numbers. Now we can use matrix multiplication for vector rotation. So let me first give you simply the formula, and then we'll go into detail how we can derive that formula. So let's say you have a vector xy, and you want to rotate this vector towards left by an angle theta to get the vector x prime, y prime. So similarly, like you had the scaling matrix we discussed in the last slide. Similarly, you will have a rotation matrix, which will do this kind of rotation. And this is the rotation matrix. We're going to explain this, how we can obtain this. But first, let's like see what's happening. So this is the desired output, the transformed version, x prime, y prime. And this is the rotation matrix. When you multiply this matrix to the original vector x, y, this is going to do this transformation. And when you do this multiplication, what will happen is x prime will be cos theta x negative of sine theta y. You can just do a dot vector between this and this. Similarly, if you multiply this with this, you will get the second value. Now let's try to understand why actually this matrix is rotating this particular vector. So before looking into a vector rotation, let's first try to rotate the axis. So by rotating the axis, what I meant is, let's say you have original axis y and then x, and you want to rotate like this whole Cartesian plane by angle theta. So this x-axis becomes x prime, and this y-axis becomes y prime. And this is like some point. We'll come back to this. Okay, so this is the point V, x, y. Now, when you rotate this axis, so the blue axis, which is like original x and y, the point was x, y, which means that the projection of this point on x-axis was x, and projection on y-axis was y. So this height is y, and this length is x. All right, and that's how we get like the vector value. Now, if we have to get the position of this vector corresponding to the transformed axis, which is x prime and y prime, again, what we'll have to do, we'll have to get the projection of this point on x, projection of this point on y. So the representation will be this distance, and the second element will be this distance. Okay. All right. So after the axis has been rotated, what we need is, I just talked about that. So x component in the new x-axis and y component in the new y-axis. All right. So we talked about vector dot product, right? And we had an interpretation there. If you are computing the dot product between two vectors, where the second vector is a unit vector, then you're actually computing the projection of the first vector along the direction of the second vector. So if B is unit vector, you compute the dot product A dot B, the result will be this projection, which can also be indicated by A cos theta. Okay, so now, so what we just need to do dot product. So we need x component in new x-axis, right? So to get that, we can just do a dot product between x and new x-axis. Okay, so for doing that dot product, we need the new x-axis and the new y-axis. All right, so let's see how we can get that. Now, so this is the new x-axis, right? And this is angle theta. Now, if you consider the original x-axis and you compute cos of that, so that will be projection of this x on x prime. All right, so which means this new x prime, which is the new axis, it has x cos theta component in this x direction. And similarly, if you compute sine theta of that, it will give you the vertical this distance, and that will be sine theta. So the new x-axis is cos theta sine theta, and similarly you can compute the new y-axis again, which will be, you can compute the so this time this is going to be theta. So the x direction value will be sine theta, and you can take the negative sign because it's on the left, and the y-axis will be the cos value. So the x-axis is negative of sine theta because it's on the left, and the vertical value is the cos theta because this is the theta angle, and you take the projection of y prime on x, that will be cos theta. Okay. Now you have the new x-axis, you have the new y-axis, and to get like the x primes and y primes corresponding to the new axis, you just need to compute the dot product. And dot product, you can use matrix representation. So if you represent these two vectors as rows of matrix, something like this, and do this matrix multiplication, so this will be dot product between the new x prime with this vector, and again dot product of this with the new this new axis with the original point, that will give you y prime. So now this is kind of your rotation matrix, which is actually not rotating your vector, but it's rotating your axis. Now, how we can use this to rotate the vector? So if you look at it carefully, when you are rotating your, if you're rotating your axis towards left, then you are actually rotating your point towards right when you represent that point on the new x prime and y prime coordinate axis, right? Because this point, it was xy in the original xy coordinate, the blue one, all right? When you rotate the axis by angle theta and you compute the representation of this vector on the new axis, which is x prime and y prime. So if you look at it carefully, it's like you are rotating the point towards right by an angle theta. So it means that you can use that rotation matrix to rotate the Cartesian plane, and you can use the same rotation matrix to rotate the point to rotate a point in that plane, but the direction will be different. It will be opposite to each other. Now, so that was like rotating in the opposite direction, but we don't want that. So we'll need like new xy axis coordinates, which will do the right kind of rotation what we wanted. Now, how to get these updated xy coordinates? So if you're rotating towards left, so that was, you are starting with blue, ending on red. Now to rotate the point to the left with an angle of theta, you will have to rotate the axis to the right. So this time we are starting with red, and the final axis is blue one. So let's see like how the coordinates are changed this time. So you're rotating with right. So if you compute the coordinates, so that will be like projection of this blue on the red. So again, so that will be cos theta. And in the y-axis, it will be sine theta, but with a negative sign because this is so this particular portion is negative, right? This is plus and negative. So this is plus and plus. This one is plus and sorry, this is negative and plus, and this is negative and negative. So we are moving in this particular direction. So it will have to be positive and negative. So when you take sine theta, the value will be sine theta, but it's in the negative direction. So it's negative sine theta, but you can do like similarly for the y-axis. This time it's going to be sine theta and cos theta. So this is positive because it's falling in this plus and plus region. So remember, like we're starting from the red one, not the blue. So the blue one is in the plus and plus region of this Cartesian coordinate. Okay. So that was rotation. Now let's talk about linear combinations. So if you have an initial vector xy and you want to perform some kind of transformations, and let's say you have some kind of matrix, so this kind of operation can give you, as you've already seen, this can give you scaling, right? When you only have diagonal, and it can help you in rotating. It can also perform skew transformations because you are doing rotation and scaling at the same time. And remember, like you can have different scaling for different coordinates. So that will lead to like skew transformation. But still we don't have any translation, like we don't have any shifting. So for shifting, we need to add some value. Otherwise, if you just multiply, it will just do scaling. So there is a hack to that. And so let's consider this updated matrices. So again, we have the same vector x, y. What we do is we just add a number 1 and make it three-dimensional. And similarly to the matrix, we add a number here in the diagonal, keeping the other two 0. So if you do this matrix multiplication, again, you will get x plus by, cx plus dy, and 1 here. So this, if you remember, this had the same transformation, which you were getting when you were multiplying with this particular matrix. So all you have to do is just ignore this number 1. So even if you have increased the dimensions of the matrix and as well as the vector, so the transformation is not changing. So even by using this, we'll still be able to perform scaling and rotation. So and also like skew transformation. Let's see how this can be used for translation as well. So instead of 0, if we add like C and F values to this particular column, so what will happen? You can do the matrix multiplication. So these are the equations which you will get. So what's happening to each of the coordinates, you are adding these values. So I'm not going to do the computation because that's fine. So you can do that, but just observe that this F is getting added to the second coordinate. This C is getting added to first coordinate. And this addition will allow you to do translation to shift your points. So we converted the same matrix, like we just updated it, we add one more dimension, and we saw that if we have to translate or shift the vector, we can just add those two values here. So now this updated matrix, this is called homogeneous system. It can also perform shifting. Now, so that was like these operations separately, but we can combine all of these together. And let's say we have to perform scaling, rotation, translation all at once. So carefully check this order. So if you have to perform this particular order in any object, so first you want to scale that object, then you want to rotate that object, and then translate that object. So the order will have to be reversed because first this matrix will be multiplied by the vector, and then this rotation matrix will be multiplied by the resultant vector. And also, like this operation, it's not commutative, because if you first perform scaling and then rotate, it will be different if you perform rotation and then scale. Okay, so that's your scaling. That's a scaling matrix. sorry, that's the scaling matrix, that's the translation matrix. And you can easily verify why this is just doing translation, because you have ones in the diagonal, right? And if you look at the matrix which we are getting, okay, let me go back. So if so D and B are 0, so you can easily ignore these two numbers. A and E are 1, so you just get X and Y. So if you have ones along the diagonal and zeros here, just C and F, then you will get A plus C and D plus F. So that's your translation matrix. Okay, so that's the translation matrix, and that's the rotation matrix we have seen, and that's the scaling matrix. Okay, so that's about it. So let's briefly also cover singular value decomposition. And I think before going to that, we need to understand what linear independence is. So linear independence, if you have some set of vectors, then, so that's like the formal definition. If you do a linear combination of all those vectors from x1 to xm, so these are the scaling factors, a1 to am, and the resultant is 0. It means that all the scaling factors should be 0. And if that happens, we call that these vectors are linearly independent. Okay, so that's the formal definition. I will give you some intuition as well why we call this linear independence. And so if it's 0, it means that, I mean, if you take any of these vector, you cannot represent that vector when you can do like any linear combination of the rest of the vectors, you will not be able to represent that particular vector. So that's like another view. And so for example, like if you have Cartesian coordinate system where all the axes are perpendicular to each other, so that's like they are linearly independent, because you cannot represent like one axis using the other. So for this, for example, so these are two vectors, they are in the same direction. So they are linearly dependent. They are not independent because you can easily scale one of the vector and represent the other one. So for example, these two are linearly independent. You cannot represent this particular vector using this vector, whatever you do, like you can do scaling, you can do anything. So now in this case, these three vectors, they are not linearly independent. Why? Because this particular vector, you can easily represent it using this vector, a combination of this and this. And that will be just like projection of this vector on this axis and projection of this on this axis. And you can say that this and this can be used to represent this particular vector. So these are not linearly independent. Again, if you have three-dimensional space, that's also linearly independent. And any two vectors, it doesn't matter like whether they're orthogonal or not, they will be linearly independent because you can't represent one of them using the other. So it doesn't matter what like the angle between them is. So it doesn't have to be 90 degrees. Okay, so that's like mathematical formulation, but let's see like how we use that when we do like machine learning or deep learning, because we use vectors to represent features. All right, and features mean they are just numbers, but eventually they represent something. So for example, we just talk conceptually, we have to solve the problem of person recognition. So if we have to recognize some person, we have to describe some features. And those features could be height of the person, it could be hair color, it could be weight of that person, whether the person is wearing specs or not, what's the eye color. So these are the features, even as a human, we use these to like recognize or identify a person, right? Apart from like facial features, that's fine. So let's see like if these features or these vectors are dependent or linearly independent. So height and hair color. So there is no dependency between these two, right? So these are linearly independent. But if we look at height and weight, there might be some kind of correlation, and if we use these to represent features for doing person recognition, it could happen that you can represent like one of that feature vector using a combination of this along with some others as well. So it will be difficult to make those linearly independent. Similarly, eye color, I think it will be independent. Now, what we want is, if we want a very good representation and we want like very compressed form of a representation, we want like all the vectors, or we also call that bases, to be independent of each other, so that we have like minimum things to store and which can represent like mostly all the features of that particular object. Now, another interesting thing, it's matrix factorization, and it has also like links to linear independence and also like feature representation. During old days, when we used to do classical computer vision, then it was used highly for classification problem and also like for feature representation. So one way to do matrix factorization is singular value decomposition. And if we have a matrix A, so singular value decomposition is like dividing this matrix into 3 different matrices. We call this U, sigma, and V. And if A is M cross N matrix, you will have to be M cross M, that's a square matrix. This will be M cross N, and V transpose will be N cross N. So these U and V, these are unitary matrices. It means like all the vectors in these matrices have unit length. And the sigma is a diagonal matrix. And so I'm not going to cover like a lot of details of this SVD. It's quite interesting, but it wasn't like very much relevant to the topics which we are going to cover this semester. So I'm skipping those details, but let me give you some interpretation of SVD. So when you're multiplying this matrix with this diagonal matrix, what's happening is you are just scaling the columns of this V using the values which you have along the diagonal in this particular matrix. So this we have seen earlier as well when we're doing scaling. All right. So what's happening is when you multiply these two, you are first scaling those columns, and then finally you are taking a linear combination with the help of this V transpose matrix. And so finally, if you try to understand this, so A can be broken down as linear combinations of these columns of U, which are scaled using this diagonal matrix. All right, and then you linearly combine with the values which you have or the vectors you have in this V. So ideally, what we do, we can use all the columns in U to represent A. But what if we don't use all the columns? We can just trim this matrix and maybe use just a few, maybe first 5 columns or so. Even then, we will be able to perform this operation. We'll have to trim this matrix down as well. So if we are using 5 columns in the first matrix, then we'll have to use 5 rows in the second matrix. And similarly, we'll have to trim down like this matrix as well. So what's going to happen is, if we use all the columns, we'll get exactly A. But if we use few of the columns, then we will get a kind of approximation of what A is. And this has a huge application in image processing. It's used for image compression. And so yeah, these columns are called principal components, the columns of view. So let's say if we have this image, and this is like 256 cross 256 image. If we represent this image as a matrix and perform SVD matrix factorization, and we try to reconstruct the image or the matrix only using few columns of U. So this is just using 20 columns from U. And you can see that it's noisy, but still we are able to recover it. But if we try to increase like these number of singular values, the quality is getting better. and by just using 85 singular values, we are getting like a reasonable quality. It's like close to the original one. And if you look at like the amount of memory we have saved, so from 256, we just got down to 85. So what this means is there was a lot of redundant information in the original representation when we were representing this image as a matrix. And what we did is we got rid of like some of the vectors in that set which were linearly dependent with the other vectors, and try to come up with linearly independent vectors, which is like the minimal set which can be used to represent the same image. So yeah, that's about SVD, and that's the end of the lecture. So if you have any questions, we can, yeah, we are already out of time, but still we can take few questions.
Sir, can you explain the L2 norm, why it is important in the deep learning?
So L2 norm, what happens is, so in deep learning, you have some network, right? And you pass some input to the network to make some predictions. So let's say you are just doing classification, all right? So for classification, let's forget about multi-level classification. Let's talk about binary classification. So you will get two values, right? Whether the object is present or not. Now, there will be a prediction from the network, okay? And then you will have the ground truth, the actual values. So to train a network, you have to compute a loss function, and the loss function will tell you like how far apart your network prediction is from the actual ground truth. And there is like lot of loss functions which you can use. So in case of classification, I mean, you can use binary cross entropy, you can use mean squared error if you want to solve as a regression problem, and you can even use L2 norm. So L2 norm will give you distance between like what you had originally, right? The ground truth and what your network predicts. So if you subtract those two vectors, you will get the difference vector, right? And you want to minimize that difference. So you can compute that difference. You can compute L2 norm, you can compute L1 norm, or you can also compute like higher level norm. So if you compute the squared L2 norm, because to train a network, you have to differentiate your cost function, right, to compute the gradients. And we will cover that when we give you the tutorial. So as I told you earlier, when you have a squared version, then computing the derivatives, it's easy because all the elements are independent of each other. So that's like one use. And I'm not saying it's a popular use, but just to give an idea. Does that answer your question?
Yes, I just wanted to know the derivative thing, like why it was important in derivative, as in calculating the gradient.
Okay, so Doyang is asking for the SVD part, does that n have a specific value? So which n? Let me go back. So where's n? You mean like m cross n? This is like just a shape of the matrix. It could be anything. Yeah, that n could be anything. You can even have a square matrix. So the example I showed, like the image, that could have been a square image, 256 cross 256. So does that answer your question? Okay.
And Professor, here U and V are the unitary matrices, right? So always the U and V will be the unitary matrices, and the sigma will be the diagonal matrices.
Yeah, that's what we aim for when we do SVD matrix factorization. That's right.
Okay. Okay. Thank you.
So any last question before we end today's lecture?
I think there's a question from Brandon.
SVD, why would you want to use a few columns of U? Okay, so the question is, I think it's a good question. So Brandon is asking, why would we only want to use a few columns of U if we have all of them? So let me go to that image. So I will give you a very practical example of this. So I think the first mission to Moon or Mars, I don't exactly remember. So it was some space mission, and there they captured the image, like how the Earth looks like from the space. And then they have to transmit that image to the Earth. So the size of the image was huge, so they can't transmit all of that data. So they performed this SVD, and they only use like first few columns of that matrix, and it's still like on Earth, we were able to reconstruct that image. So if you have to do some transmission and you want to save some kind of bandwidth, that's like one application, and it was like real world application where it was actually used. Now the idea is, so these kind of optimizations, this is like data level optimization. Of course, there's like network level optimization, so we won't be going to that. But still, if you can compress your data without losing a lot, so you're saving a lot of memory. So even if you're saving your images, you don't have to save all those pixels. So if you compute the number of pixels you require for this particular image, it will be 256 cross 256, right? That's huge. But if you do SVD matrix factorization of this image, what you're going to get is, you're going to get these three matrices, and you don't have to save all those values. Depending upon like what's your storage requirement, you can only store like a few of the columns, and so all these matrices will be smaller. So instead of saving the actual image, you can save these matrices, but when you load the image, you can just do the reconstruction and form the image. So does that answer your question, Brandon? So you sacrifice some resolution to save memory if the image is too large. Yeah, that's correct. So that's one application, and of course there are many other applications as well apart from saving memory. So we briefly talked about linear independence and all that. So if there is a lot of redundancy in your data, then it could be like you are saving a lot of memory without like sacrificing any kind of quality. So it's not only about saving memory and sacrificing the resolution. Okay, so I think we are already out of time, and thank you very much for attending the lecture. We can end it here. Right, bye.